the first talk in the evening session in our conference. Let me, with my great pleasure, introduce Professor Collin Bleak from the University of St. Andrews, Scotland, who will tell us about embedding certain automatous groups into the rational group.
Thank you very much. Thank you very much, Oksana, for the very kind introduction. I'm going to try to share my screen now. So maybe just share my whole screen. Okay. We get the actual screen. Hold on. Okay, maybe I can just get this. Can everyone see my slides?
Yes, it's great. Thank you.
Okay, great. Let me start by saying thank you very much for the organizers for having me speak. I think we have to keep shining a light, and I'm very proud and honored to be here speaking in this conference, and I'm very grateful for the organizers to let me speak here. So as Oksana said, I want to speak on embedding certain automatic groups into the rational group. Sorry, my voice seems to be a little bit gone, but hopefully it will come along. Okay, so here we go. Right. So first, my collaborators. You see Jim Belk, Indira Chatterjee, Francesca Matucci, Davide Perico. Before I even go into this, let me say that I have been traveling a lot, and I have only seen not even one half of the wonderful talks that I wish to have seen, and everything I've seen has been really fantastic. So again, thank you for this. Okay, so now I will go forward. All right, so the outline is we're going to talk about some of the motivating context and then set the frame for working on the Cantor spaces that we're studying. I'm going to give an example of what goes right and what goes wrong in our situation. And then I'm going to give the sort of at least the solution that we have for which covers things, covers quite a broad class of things. And then I'm going to maybe make some questions where we don't know the answer and we'd love to understand the answer. Okay, so the key results on the motivational context. So my collaborators and I, the result that we have is that if G is a left continuous asynchronous automatic group, then G is going to embed in the rational group. And left continuous asynchronous automatic groups don't yet exist in the literature, so we'll define what this means. Asynchronous automatic groups already do, but the adjective left continuous is new for this context. And then because of the theorem above, we have a second theorem, which is that cat0 cubulated groups admit left continuous automatic structures. This relies on some work of Niblo and Reeves together with a lot of glue. And then putting these two together, we get that cat0 cubulated groups are rational, which basically means that you can embed any cat0 cubulated group into the rational group. Okay, so these are the main results that we wish to discuss today. All right, so the motivation for us when we first got into this is that we've been steadily working on the Boone-Higman conjecture. And so this conjecture says that a finitely generated group has solvable word problem if and only if it embeds in a finitely presented simple group. And Belk, Matucci, Zaremsky, and myself have this theorem that every hyperbolic group embeds into a finitely presented simple group, getting the Boone-Higman conjecture for this broad class of groups. But this is really the first port of call because these are groups that have linear Dane functions. So it's very natural to ask about, well, what about things with quadratic Dane function or more complex groups like this? Anyway, the outline of our general proof is that we first embed any hyperbolic group into the rational group. The way that we do this is we study the Horner function boundary. We prove that the Horner function boundary in the cases that we care about are Cantor spaces, and they're the Cantor spaces found at the limit of a self-similar tree, so not even the regular n-area Cantor space necessarily, but something a bit messier, but still Cantor space. And there's always a transducer, think of it as a generalized Mealy machine, which takes the boundary of self-similar tree to the boundary of a regular tree, and then we can get into the rational group. Then we show that the embedding that we have has really nice properties when you study how it's acting on Cantor space. And we use the properties of that action to embed this new version of H into a constructible finitely represented symbol group by doing things like taking a full group on the action on Cantor space and then taking that thing and embedding it into yet another simple group. Well, that one might not be simple, so you have to embed it one more step, and we use these twisted Bryn-Thompson groups of Belk and Zaremski, and that turns out to be a very natural target. So this is our general outline. And this outline immediately falls apart when we try to go to more complicated groups. I don't know, more complicated, maybe not the right thing, but groups with harder Dane functions. So one of the places where it falls apart is that the embedding that we have into the rational group needs to be constructed in a new way. And if we succeed in making such an embedding, then it might not have the nice properties and so on and so forth. So it's an outline, but you know, there's a lot of work to be done. Okay. We're only at the beginning of a long road. Right, so what is our playground? This is something that everyone has been seeing a lot this week. So if I have a finite set of symbols, usually it's just going to be 0 and 1, and in this talk, almost always. Then I can take the finite strings over those symbols, including the empty string, and I can consider that to be a free monoid under concatenation. Then I can take any subset of that free monoid, and that's just my definition of a formal language. And this formal language might have other properties. It might be regular or context-free or arbitrary, you know, who knows? But we have a formal language in our hand. And then I can also think of the boundary. So if I think of A star as this free monoid, then it also has a natural structure of a tree where you have the finite words of the vertices and you extend a word by a letter, then this gives you an edge to a child vertex. And this is a construction we've seen many times. And if you take the boundary of that tree, then this naturally has the structure of a Cantor space, and you can just give it the discrete. If you give A the discrete topology, then you can just get this product structure for A to the omega, and this gives you a Cantor space. And then I can look, if I'm in the category of spaces, then I can look at the automorphisms of this space. So this is the group of all self-homeomorphisms of our Cantor space. And then I can look at any group, which could be a subgroup of those, so a group of such homeomorphisms. Okay, so this is our playground. This is where we're going to be doing things. Right, so as I mentioned before, we're primarily going to focus on the binary Cantor set, and we're going to denote it this way. And so here I have this tree of words that I was mentioning before, and I have some finite path to a specific word alpha, and then I have everything which extends that path, and then I have the shadow under alpha, which looks like a cone here. And so each finite binary sequence alpha corresponds to what we'll call a branch of the Cantor space, or a spherical set, if you will. And I'm just going to call that branch alpha C. And so this is all the infinite strings, which begin with the prefix A1, A2 out to AJ, where alpha is the string A1 out to AJ. Okay, so we see alpha is the string, and then we have all the points in Cantor space whose first J digits are exactly the word alpha. Okay, so this is the branch at alpha. Right, so that's going to be fundamental for something I'm going to define now, which is the rational group of Grigorchuk, Nekrashevich, and Shushansky. So they introduced this in 2000, and as Slava was saying in his talk yesterday, this is a really highly cited paper, and I think I'm helping with this thing because I love this group. This group is one of my favorite groups. I've spent a lot of time thinking about this group. I'm almost always wrong, so I have to think 2 times, 3 times, 5 times, whatever. But okay, it's really a fascinating group. So the group is not finitely generated, but it is simple. And there's a paper by Belk, Hyde, and Matucci in 2018, which gives these proofs. And it consists of those homeomorphisms of Cantor space, which are in some sense finitely definable. These are not, generally speaking, as friendly as the things that we're used to seeing with the automorphisms of trees given by these finite state machines, because these transducers, these sort of generalized Mealy machines, they are still represented by machines, but they no longer are they're no longer necessarily creating an automorphism of the tree, and I'll show you that in a second. Okay, so here is an example. Apologies if anyone has seen this example before. I could produce a different transducer, but I quite like this one. Okay, so here is a machine. I'm going to pretend that it's going to start reading the infinite strings in the state A. And you'll notice that the state B can only write 1, 0, or 0, and then other things. So the state B does not write a cone or a branch. It writes actually 1, 0, and more things plus 0 and more things. So state B is not what I would call a homeomorphism state. It's not taking a branch to a branch. Okay, it's still taking a proper clopin set to a proper clopin set. So, okay, you can tell me it's a homeomorphism and you're correct, but it's not taking a single cone to a single cone. So it's a bit strange. These machines are not as not the way you think about them. I remember a conversation when I first talked about the rational group. I had some members from this conference in there, and they were very used to automorphisms of trees, and they were trying to generate a semi-group from all the states, which you can do, but it's it's just not as friendly because B isn't acting at the root of the tree. Okay, so A does, however, A you can read a 1, and in A you can also read a 0. And my claim is that what this machine does is it starts at the root of the tree, and it will read this tile shape that we have here. So it will read 0, 0, and it will produce 0, 0 will produce a single 0. So that 0, 0 is going to produce a 0. 0, 1 is going to produce 1, 0. So this is going to produce this. And then if I read a single 1, I'm going to write a 1, 1. Okay, so what you can see is that this shaped tree becomes this shaped tree. And there's nothing here that insisted that we had to be order preserving. The way that I've drawn this, you would say, oh, that looks like an element of F. But the thing is, it's not even an element of Thompson's group F because we're going to now iterate this process. When we're all done, we go back to the state A and we repeat again. So you take your original infinite tree, you tile it with tiles of this shape, and then as you progress down the tree, you take each tile that you see that you have colored like this, and you change it to a shape like that. And so I'm going to read an infinite string here, but I'm only going to read part of it, and I'm going to slowly transform it according to the rules of the machine. And what I've colored here, this is my input, this is going to be my output. The 0, 1 that you see in the beginning, that's colored red, that's going to represent a trip from A back to itself. This is just to help us read what's actually happening. So if I do 0, 1, my input's going to go 0, 1, and my output's going to write nothing and then 1, 0. So 0, 1 is going to become 1, 0, and you see it here in orange. So I do that, and then the next thing I read is a single 1, but a 1 writes a 1, 1. So you see my red 1 is writing this orange 1, 1. And then the next 0, 1 writes a 1, 0 again. And the next 0, 1 also writes a 1, 0. The next 1 writes a 1, 1. And then I read a bunch of zeros. So every 2 zeros produces a single 0 output. So I have 0, 0, and that's going to become a single 0. That's that. And then I now have another 0, 1, and that's going to become 1, 0, and so on and so forth. So this is a machine, and it takes very long strings and produces other very long strings. And instead of thinking of it as automorphisms of the tree, you just think about the action on the boundary of the Cantor space. And one of the things you can notice about this tree is this machine, the way I've defined it, if I give you a very, very long input, then it will only produce a single very long output because I'm going to have the condition, and I haven't really made it explicit here, but I'm going to have the condition that every state only has, for each possible input letter, it has a single transition. So a 0 from A, I have a transition for 0, and I have another transition for 1. Okay, so I can read from every state anything, but I will maybe write something that's restricted. So for instance, from B, I'll never write a 1, 1. Okay, so as it happens, this machine does give you a homeomorphism of Cantor space. The bit that I was trying to make about very long strings is that if I give you a very long input string, there's only one way that it can be read into this machine. And so it's going to write some very long output, as long as I don't have a cycle that just writes nothing. If I had a cycle that writes nothing, then I'd take an infinite string, just repeat that cycle again and again and again, and I'd end up writing something finite, and this would not be a transformation from Cantor space to Cantor space. So as long as this machine is not degenerate, we're going to get a nice homeomorphism of Cantor space, and there it is. Okay, so the rational group is the set of those homeomorphisms that can be represented by such finite state machines of this type, this sort of generalized Mealy machine. I'll call them a transducer myself. Okay, so there is a more formal definition. So a homeomorphism from Cantor space to Cantor space is rational if and only if it has finitely many local actions on the branches of Cantor space. And this is why I defined branches before. So if I have some homeomorphism F, it has the same local action on the branches alpha and beta if there are other prefixes, alpha prime and beta prime, such that the image of the alpha branch under F is contained in the alpha prime branch, and the image of the beta prime branch under F is contained in the beta prime branch, and the following diagram commutes. I can go across by using F, or I can go down by doing a prefix substitution where I replace the prefix alpha by the prefix beta without making any other changes. Okay, so this basically means what F is going to do underneath alpha is the same as what F is going to do underneath beta up to some prefix exchange. Right? So you just imagine in your tree that you've got two different locations and you've got the cones under those locations, and they get sent by F into other cones somewhere else. And they may not fill the cone, but they have a map from that Cantor space cone into another cone. And maybe it's going to be some finite union of cones will be the image. And the two local images, the alpha set is getting sent into some cone alpha prime, the beta set's getting sent into some cone beta prime. And if I forget the prefixes of alpha prime and beta prime, the images look the same. So I have, the painter, which is F, is drawing the same picture locally. Okay, so these are my local actions. All right, so this is the rational group. And as I say, it's quite fascinating. And the local actions basically correspond to the states of your transducer. When you're trying to build the transducer, each local action will give you a different state. Okay, so that's it for rational group for now. I'm now going to talk about what are automatic groups. And I have left here because automatic groups always have a sense. Either you're approaching them as a left automatic group or a right automatic group. And the definition depends on which one you choose. Any group which has a left automatic structure also has a right automatic structure, so this really doesn't matter. But you have to make choices when you're giving your definitions. So what is an automatic structure on a group? So we're just going to recall that. So a group G admits a left automatic structure if there exists a finite subset of G which generates G as a monoid. So, one way to do this is if you had a sort of standard generating set, then you could just take its inverse closure, and now the set with its inverse closure will get generated as a monoid. I see there's a question in the chat. Okay. Oh, thank you. I'm very happy you love the sunflowers in the background. That's wonderful. Okay, so yes, I'm watching the brave folk of Ukraine all the time, and I'm impressed for the light of the world that people will stand up for what is right. Anyway, so back to the talk. Sorry for this distraction. So a group G admits a left automatic structure if there exists a finite set which generates it as a monoid. So again, you can just take a normal generating set and add its inverse closure, and this is going to now generate your group as a monoid, but you don't actually have to have formal inverses. A finite group, you could just take every element of the group is going to generate it finitely, but you could actually just, if you took something that has finite order, you raise it to high enough power, you get to its inverse. So you don't actually need the inverse. You could just start with the one side, and that's already going to be able to create the inverse for you. Okay, so we want to be able to generate G as a monoid. And we want to do the following. So we also have a word acceptor, which is an automaton. So this is a finite state machine that determines an accepted language for the group. Okay, and I'll give you an example of this, time allowing, on a side page. All right, so a word acceptor automaton, which with accepted language L, it's a subset of A star, and it's going to accept for every element of G at least one string and A star representing it. And so this is going to give you what's a regular language representing the group elements, possibly not unique. Then there's going to be a further set called multiplier automata. So the elements of this set actually are automata, and they're very strange because they tell you how to multiply. So a multiplier automata M sub A is going to accept a pair of words W1 comma W2 in my language squared, precisely when if I left multiply A by W1, then I'm going to get W2 in the group. So this is why we're doing a left automatic, because we're having a left action by our generators. Okay. In this case, once I have my generating set, my language automaton, the word acceptor automaton, and all the multiplier automata together, then that together forms what's called a left automatic structure for the group. Okay. And a group is left automatic if and only if it admits a left automatic structure. And there's all sorts of things we can say about this. If you're left automatic with one generating set, then you're actually left automatic with any other finite generating set that you care to name, and all the sort of standard things that you might expect to be true for geometric group theory generally hold. So here's a little bit of history of these things. So the history of automatic groups, or they were created in conversations between Cannon and Thurston. And basically what was happening was Cannon was having a lot of results in thinking about Kleinian groups, and Thurston was understanding that there were ways to do these calculations. And so in these conversations, Thurston actually put forward the definition of automatic groups, but they arose from these conversations. And then shortly afterwards, Epstein was able to prove that automatic groups are finally presented. And then Thurston was able to show this shell construction, which basically shows that each automatic group has a quadratic Dane function. And normally in a talk on automatic groups, one is obliged to give the shell construction to explain the quadratic Dane function. But instead, I'm going to just refer to the book, which is coming up. Anyway, multiplier automata are going to help you do calculations in these groups. And the standard initial reference for this is this very well-known book, Word Processing on Groups by Epstein, Cannon, Holt, Levy, Patterson, and Thurston. And it will contain all sorts of nice constructions. Anyway, Holt and Epstein have gone on to show many different algorithmic procedures to find automatic structures on finally presented groups, but it's not, it's not a guarantee. So there's lots of open questions that remain. And I'll get to one of those in a second. But a really nice result from 1998 is that Niblo and Reeves were able to cubulate. They were able to show that cubulated cat-zero groups are not just automatic, but a stronger form of automatic called biautomatic. And so this is a really, really nice result. It's a broad class of groups as well. And many questions remain, but really they're not very easy. So for instance, nobody knows if you can put an automatic structure on Thompson's group F. This is a big open question. Okay, so just to sort of tie in a little bit this hook with the cubulated cat-zero groups, I want to talk about them just a bit. So a cat-zero group is a finitely generated group that acts geometrically, so geometrically proper, co-compact, and biisometries on a cat-zero space. So a group is cat-zero cubulated if it acts just as I said before, but not just on a cat-zero space, but on a cat-zero cubical complex. And you might ask me what's the difference between a cat-zero space and a cat-zero cubical complex? Obviously, it involves cubical complexes. But before I get into some of that geometry, let me just mention some examples of cat-zero cubulated groups are surface groups, hyperbolic three-manifold groups, right-angled Artin groups, right-angled Coxeter groups, and the Berger-Moses finitely presented symbol groups. So there's a lot of groups that fit into this classification. So coming out of Segeev's thesis and some of his papers, so here I have some cubes over on the right-hand side, and I'm going to tell you how to identify them. And there are forbidden geometry. These are, if you make identifications according to these forbidden geometries, then you're going to get effectively positive curvature, and your resulting space will not be cat-zero. So if you identify these two sides, you get this structure, and the link around the vertex V would look like this circle. If you identified this, then it's like you're folding two sheets of paper together and gluing two of their edges too closely, and the link looks like that around the vertex. If you glue three together this way, then you get this. So these are all the forbidden geometry, because if you have this geometry, you have strong indicators of positive curvature, essentially. All right, so a cat-zero cubical complex will be a cube complex that doesn't have any of this kind of forbidden geometry to it. All right, so here are some good cat-zero examples. The first one's given by Segeev. If you were to take two trees and you take the product of the trees, then you get a nice cubical complex structure. It's very beautiful. And if you were to take the link around any of these sort of vertices, then you get some nice structure, and the link is not forbidden. This second example is much more naive. This is an example where, from the hyperbolic groups paper that I mentioned before, where we've glued together a bunch of squares, but we're putting 5 squares together at every vertex, and so we get end up getting a hyperbolic structure here. And so this is here's a cat-zero cubical complex with negative curvature, and naturally the group of actions on it is going to be a cat-zero cubical complex group, and it's a hyperbolic group, and okay, so there we are. Right, so what was the big deal? Why am I sort of going on about the Niblo-Reeves result, other than the fact that it's an amazing result? Well, in their construction, what they showed is that if you have a cat-zero cubical complex, then there's a very natural language for the calligraph. So if you choose some nice generators, and what you want your generators to do is for every cube, you want to have a generator for crossing the cube in any of the core directions, including the diagonals. And you want to imagine that the language that we're going to use is going to be the language for cross the highest dimensional diagonal that you can at any one time. And we're thinking about geodesics here, so you don't ever want to cross a diagonal and then cross a different diagonal, which will allow you to cross the same horizontal hyperplane, because then you would have had a path that went across the line and came back across the line. It wouldn't be efficient. So you want to have paths that never cross hyperplanes twice, and where you're always going over the highest dimensional path you possibly can. So here I have a picture of the Z squared lattice. My generators are up, down, right, left, and the four diagonal motions. And every point on the Z squared lattice has a unique path from the origin to that point, where I go the highest dimension path that I possibly can until I can't anymore, and then I tailor off to something horizontal or vertical. And so I get this nice tree structure. This is a structure. This describes the lattice of points. This gives me all the points in Z squared, but it gives me a unique path to those points from the origin, and that gives me a word in my generators. And so if my generators are these, then I can have a unique word representing every element of Z squared. And so this is a language in this generating set that gives us normal forms for Z squared. And indeed, here is an automaton which accepts exactly that language. The green state is the initial state. All of these blue states around the outside are other states. Every state you see here is an accept state. So if you start in the initial state and you take any journey on this machine, then you concatenate all the edge symbols that you see along the way, and you're going to have a valid word in the language for this machine, and that will precisely give you a unique representative for every element of Z squared in this picture I have here. Okay, so this is how computer scientists like to determine their regular languages. They have a machine, and you look at all the paths in the machine whose decoration, every path from an initial state to an accept state, and you concatenate the decorations, and then whatever that concatenated decorations of the edges are, that gives you a word that's accepted by that language. So here we have exactly that context. All right, so so if we want to have a left automatic group structure, now we understand what the multiplier automaton does. We understand what the word recognition automaton does, but we don't really understand the multipliers yet. And we'd like to understand them. So what you're supposed to do is you're supposed to take two words, U and V, and you're going to multiply the U on the left by A for the generator A, and you want to land in the language. And so the way you're going to represent this, the edges of this machine have to actually be given by pairs of letters. You're going to have a U letter and a V letter. So we want what's going to get accepted here is a string that looks like this, or like this, or like this. If the U word is longer than the V word, you have to have some padding letters, some padding symbols. If the V word and the U word are the same length, then your string will look like this. And if the V word is longer than the U word, then your string would look like this. Hi, Oksana.
No, it's good. Continue.
Okay, okay. So this is what my edges along my automaton. So I have my multiplier automatons basically accepting strings that look of this type, and this characterizes exactly what your multiplication is doing. All right, and so this is clear enough, and so this is what the multiplier automata do. All right, so we would like to build from a multiplier automata what the transducer is, but there's a problem, which I'm going to mention. So transducers usually act on Cantor spaces, and they respect the topology, but the multiplier automata don't have to admit necessarily infinite paths through them. They could be really messy. You don't have any guarantee that you're having some kind of cycle or anything of this nature. Also, the multiplier automaton, we want to use it to transform an infinite input to an infinite output, but we need that long common prefixes map uniquely to long common prefixes in output. And that might not happen if your language is bad enough. Okay, and then finally, the K fellow traveler condition. So I didn't mention this before, but another way of thinking about automatic groups is this thing called the K fellow traveler condition. And what it says is if you're reading a long word in the multiplier automaton, basically what your input is going to be distance K in the calligraph from whatever your output is. And so your inputs and outputs are going to fellow travel together. And this ends up being the core thing for the shell construction. But what it means for us is that you shouldn't need to have infinite information about your input string to know what to write. You only need a finite amount. Okay, so I'm just about done. So we're left continuous if we do everything we did before. However, we need that the multiplier automaton is going to induce a continuous homeomorphism on basically the set of accumulation points in the minimal subtree X star containing the elements of the language as your vertices. And you might think that that's not going to be a big deal, but here I'm going to give you a language for Z squared. There it is. And if you think of A's as going left and right and B's as going up, this is a nice, unique description. This is easy to get accepted by an automaton. So this is really a formal language, a regular language. But I have the problem that if I have an input string of infinitely many B's, or like say 1,000,000 B's, and you want to left multiply by an A, if I don't have any A's at the end, then I'm just going to go A and then write my many B's. But if I have an A inverse at the end, then I'm going to go all my B's and then cancel the A inverse. So that means I don't know what to do with my initial A. Do I prepend it or do I cancel something later? And I have to go for a very long time and not know the answer. So this is something that will not, I can have two strings with have 1,000,000 B's, and I don't know how to multiply them by A on the left and get the same long common prefix in the output. So this is the issue. So these bad structures exist, and this is what we had to solve. And so the solution is, by definition, you're going to be left continuous automatic if you have a structure where this doesn't happen. Okay. And the point about the Niblo-Reeves thing is that the normal cube path thing is exactly such a structure. So if I have cat zero cubulated complexes, the normal cube path structure that we talked about is such a structure where if I do left multiplication, I actually have enough information to resolve everything from the prefixes. And so we have these guys solved. All right, so our theorem, again, just finishing up. Your left continuous asynchronously automatic, then you embed in the rational group. Cat zero cubulated complexes admit left continuous automatic structures, even better than asynchronously automatic. And as a corollary, cat zero cubulated groups are rational. And we still do not know how to answer if a group is left automatic, must it admit a left continuous automatic structure? And I gave you an example with Z squared, where we gave you an automatic structure that doesn't have a left continuous automatic structure, but there was a different structure we could have picked that was left continuous automatic. And so that's everything I have to say. Here's a model automaton that we get that actually makes a transducer out of a multiplier automaton after a lot of work. And so that's really everything. Thank you very much.